On behalf of Space Education and Research Foundation, and on my personal behalf, I am very happy to welcome Dr. Megha U. Bhatt, the speaker for this webinar on remote sensing of planets. This is the third talk of this webinar. The earlier two talks you have already listened by Dr. Megha Bhatt. But those were recorded version. This talk she is giving, actually she is now present in the room and she will give it live and answer to your queries of uh, last two talks as well. So before I hand over the mic to Dr. Megha Bhatt to start her talk, I will briefly introduce him to you. Dr. Megha Bhatt is at present a faculty uh, in the Planetary Science Division of Physical Research Institute, Ahmedabad. This is a unit of Department of Space, Government of India. She had a very excellent academic career, did her BSc and MSc Physics from Rani Durgavati Vishwavidyalaya, Jabalpur. And after that, she went to Germany and joined Max Planck Institute for Solar System Research and did her PhD there in 2012. During her PhD, she developed a new iron estimation algorithm using multispectral data from infrared spectrometer 2 or SIR2 on board Chandrayaan-1 mission. And her research focuses mainly on the evolution of solar system. She studies for this the surface composition of airless bodies. Particularly, she has been mapping the major lunar elements and mineral exposures there. The topmost layer of the moon surface provides insight mechanism which govern the formation of moon and the subsequent internal differentiation of that. Her major interest lies in the spectrometric observations in visible and near infrared emissions. So with these few words, I now request Dr. Megha Bhatt to start her presentation, and I myself will leave the room and listen to her talk. Dr. Megha Bhatt, please.
So thank you very much, Dr. Hariom Vats, for this introduction. And I'm really sorry that last two talks I could not give being present in the room. But I hope that it was a good introduction to comparative planetology and basically the reflectance spectroscopy, what we use as a tool to explore the surface evolution processes. Now, and I'm really sorry, there is some construction work going on, so you may actually find some strange voices in between. We have already requested them to minimize it, but obviously they can't stop it, so it will be there in the background. But I hope it won't be too disturbing to us. So the title of this talk is Remote Sensing of Moon, and as basically we are going in a very basic level because all of us are having a different level of understanding and a different level of interest. So the idea of this series is to give you a very basic information from where you can actually start. So it's like once you have a specific interest, you are always welcome to contact for further information if you want, or you can actually send your questions, which I will be always happy to answer. So basically, let's start with first of all that the moon, basically, if you see that this is the only body from where we have actually samples from geologic context. So basically from known lat long coordinates we have samples. This is the only planetary body so far we have plans to get samples back from Mars in near future, but for now this is the only body. So basically we can say that the moon is the most explored object of our solar system. So from very beginning time itself, because human we are by nature very curious, so we used to like I mean we have records from our very old literature that even before invention of telescope, people were always puzzled seeing moon on sky. uh, so we from that time itself we started understanding our neighbor. So then we have actually telescopic studies from moon. So we a very extensive database we have already created for moon uh, morphology and different kind of features what we get, and we are based on those images, based on observations in different wavelength ranges, we already have some kind of good understanding. But still this object actually attracts us because this is a kind of a um, laboratory. It's a natural laboratory where you can go and can actually get records of early solar system. uh, Except telescopic observation, now we have a range of space flights starting from Luna 1, and the recent one is Chandrayaan 2. And that not only orbiters, but we have also landed on moon. We have, as I already explained, that we have samples, return samples from moon, and we have, like as you know, that China moon mission is already going on, and one rover on the far side of the moon is exploring the surface of the moon. So, and then in the near future, there are many other missions, not only from national agencies but also from private agencies have been planned. So moon is basically a very kind of, say, you can say that it's the exploration since beginning till now, and even in future, lot of other missions have been planned. So you can see that a wealth of data we have from moon, and still there are many open questions which still puzzles us, and that is the main motivation that why we are still sending missions to moon. So just a very basic things about like moon. The first thing what we observe is that we always look to the same side of the moon. So why it is so? Because that the main reason is that the moon spins on its axis uh, once every 27 days, and this is the time it also takes to complete one rotation of earth. So for example, that earth rotates in its own axis in 24 hours. So basically, because moon is kind of if you consider this as earth and this is moon, basically it's rotating around earth, and at the same time it's rotating in its axis. This is a kind of a tidal lock, which actually is responsible for why we see only always the one side of the moon. So obviously, because we see one side of the moon, we have named it as near side, or sometimes people say that other side of the moon, which we also say as far side, is actually a side which is known as dark side. But basically, this is not a dark side, because literally dark side means that if you are not getting sunlight to that, but that is not the case. The far side of the moon also gets sunlight. Those are also the illuminated surface, but only thing is that we can't see the far side of the moon. So until unless we do not send orbiters, so the first far side image was actually recorded by Luna 3 mission, and that was the first time when we actually came to know that the near side and the far side of the moon are very different. So I have a slide explaining that also, but just we go in the order. So if we just look through telescope or even through our eyes, if we see some differences in reflectance or some differences in its albedo, and that is actually, that itself is a kind of a first question to address, that why do we see those differences. So this is just a telescopic image, and I have just marked that we have these two kind of terrains. First, this is called highland, which is actually bright, and then we have these dark patches, which we say as mare. So this is a location of Mare Imbrium, one of the actually in the near side of the moon. You can say it's a huge impact happened, which was later on flooded by lava of the composition, which is like rich in iron, and that's why you can see the color, which is actually dark. And then within this also you can see some very fresh craters, as I have marked here one crater here, which again is bright because it is bringing up the material which is actually young. So that's why you can see that it has some ray features also. So this is overall like how the near side of the moon look, and I really encourage you to look moon through telescope. If you have not done so far, you should look, because some of the craters like this crater or this crater Tycho, actually you can really see details. Even you can see central peak of this very well through telescopic images. So I really encourage you to have a feeling of its morphology. You should actually look the surface of the moon through telescope. This is another image. I'm just showing you that how nicely the texture and the structure, actually even just by a telescope you can look. And this is not a very high resolution telescope. With a, say, with a nominal kind of telescope itself, you can actually, even with your binocular, very good binocular, actually you can look to, because it's not too far to us. So that's why it's a advantage for us that we can actually explore our only neighbor in a very fine way, as well as a very crude way. So if we see, if we compare near side and far side, this is how it looks. So before sending orbital missions, our understanding was that the far side should also be very similar to near side. But if we compare, it is not the case so far. So in near side we have lava eruption, but in far side, if you compare, it is mainly dominant by craters. So there is a asymmetry between near side and far side. There are certain explanations for this, but still we are still, this is a kind of an open question which we are still trying to address using the new data set what we are collecting since past decade. So basically what you can see, if you just compare near and far side, everywhere you find craters on the surface of moon. So it's very important to understand how these craters formed, what does crater mean, what the diameter of crater, is there any relationship between the impactor and the crater. All these things we have to understand in order to understand the overall surface evolution of the moon. So now if we go little more in detail, if so we have in the from 1990s, first time we had the global elemental maps of the moon. So here what I'm showing you is the iron map of the moon, and very immediately, like when you see this iron distribution, what you can see is that there are certain patches which you can actually group. So this can be one patch, then this can be another patch, and here is another patch. So basically what we say, based on the overall content of iron, just by one element, actually we can say that the terrain of moon can be divided into three groups. And the most of the surface, as you can see here, is actually this ferron anorthosite, which is the 80% of highland crust, and this is the oldest surface, which has 80% of calcium rich plagioclase and low magnesium pyroxene. Whereas there is another region which is actually, we say that it is also old, but it is younger than this ferron anorthosite, and this has higher magnesium content. Another thing what you can see here is actually Procellarum creep terrain, and that is basically rich in potassium. So creep is a short form of potassium, rare earth, and phosphorus. So this what you see enrichment of these elements in a specific part of the moon. So why is so? Why this is only confined to this area? So there are some explanations, but again, as I said, that with new data sets and with new missions, we are still exploring and trying to find out the final answer to that. So basically what we know is that this kind of I mean, based on our modeling approach, we know that this could be the result of final 2% of melt phase from the crystallization of magma ocean. So I think in the last class I covered that the mark basically the any planetary body in initial time you can consider it as a in a molten stage, and then the crystallization starts. So the heavy elements sunk to bottom and the light elements cover up on and float on the top. So basically when you have this radioactive elements which has heat that can again actually melt the some part of the area, and that can actually change the and that melt again gets crystallized, so that gives a second order of crystallization process, and this is actually that this is the result of that complicated process. So if we look to, so this was about the terrains, and then if we look at how probably it would be looking just after bombardment, this probably this is just a imagination, or just based on our observations and models. We know that initially probably after bombardment moon, probably the surface would look something like this, and then because of the partial melting in deep of the interior, uh, uh, this diverse mineralogy zones formed, and due to these impacts which actually provided way to bring this lava on the surface. So basically this eruption probably happened for more than a, so it's like a long process which actually happened, what we know is for more than 1 billion years. And this is so impact processes are one form of modifying surface. Another thing what can actually alter the surface is actually the space weathering effects, which also very briefly we discussed in last talk. So I will not go in that again, but basically this is solar wind particles, which actually, because it doesn't have a magnetic shield, it keep coming and impact on the surface, and long term impact of this particle actually result in some modification process of the surface, which actually at long run actually alters the surface along with the impact processes. So these are impact governing and space weathering governing. These are the two surface modification processes works in case of moon, because there is no climate, no seasons, so it is not affected by any other processes which actually are dominant in case of earth. But in this case actually what is dominating is actually impact processes. So so another thing what, so we just talked about Mare, we talked about far side, but the main interest for recent mission is actually poles. So polls are still, there are many open questions which we have to answer. The first time actually we started getting interest in kind of pole exploration is from lunar this LP mission. So basically, at the same time, around 1998, when we got the first polar maps of hydrogen. So this, what you are seeing, is north pole of moon, and this is the south pole of moon. And what we saw was that based on the if you have this, I mean, if you map the neutron flux, actually what you see that there is a decrease in intensity of epithermal and fast neutron, which is an indication of hydrogen. So from this mission, actually we knew that there is hydrogen present, but in which form? Is it in the form of hydroxyl associated with minerals, or is it in form of ice? So that this instrument could not tell us, and that's why that was the major motivation to plan Chandrayaan 1 mission, because we wanted to know that hydrogen is in which form available. And actually with our SAR experiment and with moon mineralogy mapper, actually we could come up with some estimation and detection in the way that now we know that there are places where actually we have exposure of ices. And this is a recent study which actually provided first map of ice exposures on poles, and there are like some areas which do not get sunlight. So because of the tilt of the moon, it is about 1.5 degrees. So because there is it's almost kind of a vertical axis. So some areas are in permanently shadowed for billions of years. So because the axis changes slightly in a long run, but at least we can say that some part of moon has not seen sun for at least a billion or 2 billions of years. So these are the areas, if you keep, these are the kind of freeze where you, if you keep water, it will be in the frozen state for as long as it do not see sunlight. So basically these are the areas of most interest, both scientifically as well as from exploration side, because you do not have to dig the surface to get water. If you just go there, you have the ice exposures on the surface itself, which can be actually utilized for our future missions. So basically from 1998 1999 missions, we did not know that in what form hydrogen is present. Is it water ice, or is it in form of organics, or is it like protons captured by solids? So and how large are these resources? So basically our recent mission Chandrayaan 2 is actually this is one of the scientific objective of this mission, where we really want to quantify that how much is present. So we have estimation, we have detection, we have identified that there are ice exposures, but how much, that is the quantification we are planning to do with our new in present Chandrayaan 2 mission. So just to summarize, and this I showed in the first presentation also, that if we see that we have actually covered almost all planetary bodies through spacecrafts, but if you consider mainly our this moon, our own neighbor, we have a long list of spacecraft and long list of missions. Some of them are manned missions, some of them are orbiters, others are landers and rovers, and there are few planned in a very near future. So this is a body which is which keep attracting us, and there are many questions which actually, and not only for our solar system, but even to understand our own earth evolution, actually it is necessary to go there and explore. Because in case of earth, we do not have evidences, we have lost evidences, but moon actually keep every scar as it is on its surface. So every scar actually has a story to tell. So if we just summarize that how many I mean, from the early time, actually USA had total 31 attempts. Out of that, 22 were successful, and USSR actually had 48 attempts. Out of that, 21 were successful. And here you can see the landing sites which we have actually. So most of them, you can see that are actually from equator. Some of them were actually from the far, I mean, the edge of near and far side. So we had few samples returned from this area also. And with Chandrayaan 1, actually the idea was that if you see here I am showing all landed missions, and then with Chandrayaan 2, our plan was to land in the southern latitudes where okay, somehow the position, yeah, I mean, it's a little up here, and that what you can see here as a enlarged image, and this was the basically identified landing location. uh, but unfortunately we couldn't land there, but this is the kind of a first attempt where we tried to land in the polar region in the near side. Then if we because we have many missions, we have actually very good data collection in terms of I mean, so not, I mean, data collection from so in the last talk we covered this part where like we have where I showed that the coverage of wavelength depends on your scientific objective, so what exactly you want to do. So in case of moon, because it's an airless body, the observations are less complicated as in case of Mars or Venus. So basically from telescopic observation we have topography, multispectral, albedo, then we have laser ranging again to have idea about topography and about gravity. Then we have charged particle spectrometers, radar sounders, magnetometers, plasma imagers, microwave radiometers, neutron detectors, cosmic ray telescopes, gamma ray spectrometers, X-ray spectrometers, multiband imagers, and spectral profiles. So basically, if you see that we have actually a very good coverage starting from gamma ray up to like going towards shorter wavelength ranges. So basically, we are covering a full electromagnetic spectrum, and this is the place from where we have samples from collected from a known latitude and longitude, as well as we have indirect samples in terms of lunar meteorites. So this sample collection is actually confined to equatorial region, but this actually provides us a good range because this meteorites can be from any part of the moon, but the only problem is we cannot relate it to that from where exactly it is coming. So that's a limitation of lunar meteorites. But obviously in terms of composition, as we are restricted here, we can see actually overall variation in if we study lunar meteorites. And then obviously we have remote sensing. So this is a kind of a favorite object for remote sensing observations. So then we have explored, but still we want to know, so why so? So just to summarize that this is a dusty window to the Earth's past. So for again, as like we do not have evidences on Moon, but on sorry on Earth, but the evidences are present on Moon. And as we have samples, we know that Moon and Earth almost formed at the same time. So whatever actually impacting to moon was also actually impacting to earth at almost the same time. So the bombardment history of the inner solar system is uniquely revealed on the moon, which actually help us to characterize and date the impact flux of early and recent inner solar system. This actually has important information about early Earth and origin of life, because it has record on solar variations, cosmic dust inputs, unmetamorphosed morphosed samples of early Earth surface. Then impact processes on planetary surface. So we are, whatever we are learning in from moon, actually we are applying to other planetary bodies, or at least to other airless bodies, or bodies with very thin atmosphere. So it's very important to um, understand the processes going on moon, so that that can be actually uh, kind of relate with other planetary bodies. So just a very simple comparison between Earth and Moon. So Moon is about 1/4 width of Earth, and it has 1/6 of Earth gravity. The major differences are, like in case of Earth, we have water erosion, we have wind. There is no water erosion or wind in case of Moon, obviously because there is no atmosphere, so we do not see this kind of alteration processes. Impact happened in case of both the bodies. As I showed one example, Beringer crater, what we can actually explore on Earth surface. In our India itself, we have a crater, Luna crater in Maharashtra, which we can actually explore. So there are impacts in case of Earth and Moon, but in case of Earth, because it's a active, geologically active body, the evidences we eventually lose. Because of the plate tectonics and many other activities going on. So obviously the result is there are few craters, something like in hundreds what we know, but whereas the moon is full of craters. Wherever you look, actually moon surface is a crater, 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 crater within crater, and then again crater. So it's basically it is like full of craters. Here we have active volcanoes on Earth, but we do not have any evidences of active volcanoes in case of Moon. There are earthquakes. There are small moonquakes also, though it's a one planet, one plate planetary body, but there are some kind of vibrations which actually generates small moon quakes. So some kind of shakings because of the impacts actually. So when impact happens, there is a because it happens in a very very small scale, the energy is transferred, and that actually creates some kind of shaking. There are some evidences of internal shaking also, but we won't go in that detail. Then we have active magnetic field on Earth, whereas we do not have any active magnetic field for now on Moon. There are some patches of magnetic field, what we say that magnetic anomaly regions on the Moon, but we do not know that if Moon had at a certain time active dynamo, or was the Moon was fully covered by magnetic field at some certain time in the past. Then, as we already discussed, Earth has plate tectonics, whereas Moon is one planet system. Earth has a lot of liquid water, whereas there is no liquid water on Moon. But now we know that there are ice exposures at poles in shadow region. So basically, if we have to summarize, we can say that Earth is a geologically active body, whereas Moon is a geologically inactive body. So what we knew from our early phase of investigation, from landers and from basically Apollo and Luna missions, when we got samples returned to Earth, we from the lab analysis of samples, we knew that Mare is younger in comparison to Highland, and this material is actually volatile free. Then from photos we know that Mare areas are have morphology of lava floods, whereas highlands are heavily cratered by impacts. And before this orbiter missions, we also had, there was second thought that all the craters probably are volcanic in nature. But then, after having images and after having sample written, we know that the main source of having these craters is actually through impact, and it's not from the lava, or not from the volcanic origin. And basically it's a differentiated planet. So before Apollo sample return mission, we did not know if this is a differentiated planet or not. But after analyzing samples, now we know that it's a differentiated planet, and the crust is about 50 to 100 kilometer thick. The crust thickness varies from highland to mare, and this is a seismically quiet and quiet body, which actually experience sometimes very faint deep quakes. So the result of this initial or the first phase of exploration was that we had some understanding on how the moon actually formed, or the moon earth system formed. So the this is still a hypothesis, but this is the most likely and the most accepted way of formation of moon, and it's known as giant impact hypothesis. So we will spend some time to understand that what is this giant impact hypothesis. So before Apollo missions, there were three possibilities proposed. One was fission, where you have Earth, and from Earth some bulge of some area actually eventually separated from Earth and formed Moon. So this one was the first hypothesis proposed. Then, but we saw that there are some differences between Earth and Moon, and if the differences are there, it means that the body should be evolved in a different way. So this hypothesis could not explain that. Then came another hypothesis, which is a capture hypothesis, which tells that basically Moon formed somewhere else in the solar system, which was eventually captured by Earth, and that's why the chemical composition difference, what we see in case of Earth and Moon. But there are certain similarities also, and there is a angle which actually could not be explained through this hypothesis. Then came the third hypothesis, accretion hypothesis, which tells that the Earth and Moon actually formed at almost the same time at the same region of solar system, and the Earth was in a kind of a the Moon was in form of debris around Earth, which eventually actually eventually it actually formed this got accreted and actually formed Moon. But this again, I mean, each and every hypothesis could explain certain part of similarities and dissimilarities between Earth, but could not explain all the observations we had. Then came this giant impact hypothesis, and because this is the most probable scenario what we are thinking about, I will explain it in a little bit of more detail. So basically, the question what we have to ask is, where did the Moon come from? So basically, all the question is that are the Moon and the Earth are made of same material? So we have certain understanding there is difference between Earth density and Moon density. Moon is actually depleted in volatiles, and it's enriched in refractory elements, and it has high angular the system of Earth and Moon has high angular momentum. So basically, all these features or all these properties, if a hypothesis can explain, probably that can be accepted as a theory. So what we actually, this is just some screenshot of a model proposed, where we have, initially we assumed that there was like debris in the solar system, and then the planetary system started to form through accretion. So the small molecules then started to get combined, and slowly it became planetesimals. And this at this time, actually, when Earth was in form of I mean, we say it was a prototype Earth, where it already had some level of differentiation between core and mantle. At that time, a Mars-sized body called Theia hit the Earth at a certain angle, which actually, and that the impact was so huge that almost full Earth, or maybe the half of the Earth, was again in the molten stage, and some debris which actually scattered and actually came in the orbit to Earth, and finally it again started condensing, and it actually formed Moon about 4 billion years before 4 billion. And once it was in the, so before getting condensed, it was in the form of molten stage, where again, because this was a very chaotic time of our solar system, when many small bodies were actually hitting to each other, and basically planet had to clear its surrounding to be a planet. So if by definition planet should clear its surrounding, so all these small bodies were actually impacting to Moon, and this is a time of the solidification of magma, when already these impacts are happening. And then this heavy elements started to sink in the and then the light materials floated, and then actually that formed the primary crust of the Moon. After that, again, though now the frequency of impact actually started to reduce, but there were some major impacts, and one of them is the South Pole Atkin Formation, which happened almost at 4.3 billion years. And that actually kind of removed the first layer of the Moon which formed. And then along with this, many other big impacts were happening that actually formed the basins during this time. So Moon formed around 4 billion years, and then this basin started to form around 3.9 billion years, and then this volcanism continued for another 1 billion years. And then this is how the Moon looked about 3.8 billion years. And then again, after this layer of, so let's say the secondary crust of the Moon already solidified, and still the impact cratering impact processes were dominating. But now the number of impacts as well as the size of impactor is actually reduced, and that's why we started getting smaller impacts and not very huge impacts. Some of them are very huge, but most of that what we see is actually small, and this is what the present day Moon look like. So now the frequency of impacts is very less, but there are still I don't remember by heart, but at least few impacts per year happens, which actually makes the scar on Moon. And there was a project, Moon Zoo, where actually you have all images from Moon, and you just, what you have to do is you have to compare Moon images from old time and now, and see that if there was an impact which actually created a new crater, or or it at least removed the first layer and showed some fresh material on top. So basically, if we summarize that what we know about origin and interior of the moon, we know that there was some kind of giant impact. There are many still open questions which this giant impact hypothesis is not able to answer, and that is again why we this is not considered so far as theory, because until unless it do not actually explain all observations, we can't actually consider it as a theory. But what we know for sure is that moon was molten at maybe we do not know the depth, maybe maybe the whole moon was molten, or maybe up to certain depth it was molten. But yeah, I'm giving a webinar, I just come to it. Then so what we see is that in the x-axis is a timeline. So this is present time, and this is the time moon formed. So initially it was in the molten stage, and then the primary crust formed. And then obviously this olivine and pyroxene, the heavy iron-rich minerals, basically sunk in the bottom, and the topmost layer was formed by anorthositic crust, which again got fractured. And from this fractured area, we got the channels from where this partial melting could actually come on top and could flow and could make the plain areas on moon. So basically, from 4.2 to 3, about 2 billion years, this process continued. And after that, there was I mean, this is the understanding actually we have contributed from Chandrayaan-1, that some very recent volcanism also happened and observed on moon. But this is a kind of a general understanding that after 2 billion years, this volcanic activities stopped, and the surface, what the thin regolith layer formed, which actually then whatever changes happened after that is actually mainly the contribution of impact craters and space weathering effects. So basically, if we say broadly, lunar crust can be divided into primary and secondary. So what we can say is that the crystallization is in bottom up format, and the mainly the the topmost layer is comprised of aluminium and calcium, which is actually light materials. So this is maybe I will skip this slide because we do not have enough time. Just what I want to convey from here is that the first layer is fine regolith. After that, if you go little deep, you have large scale ejecta. Then if you go further deep, we hope that we have the structurally distributed crust, and at the end, after about in the depth of 5 to 7 kilo, sorry, this is the sound velocity, but at a certain depth, what you get is actually the fractured crust. So, and just to remind you that whatever samples we have collected or whatever analysis we do is actually from the topmost layer. So even if with radar we can't penetrate too deep, and we can't get actually the information of this part of the moon. So far we do not have that. So this is just to give you some example of morphology. So as I already said that morphology is mainly dominated by craters. Here this is a globe centered at South Pole Aitken Basin, and you can see that everywhere there are craters. And this is a Apollo 11 image taken by astronaut, and what you can see that even within this, when in a very fine scale, if you see that there are structures which are like some small craters or some boulders, and so it's actually not as boring as people used to think in beginning. So moon has like many interesting features, and interesting still many interesting open questions which we have to understand. So just maybe one or two slides on morphology. So basically you can get craters of several different sizes. So here you can see as the size increases, you see the difference in morphology. So the simple crater do not have this kind of floor feature, and then as the size increases, you start seeing the central peaks coming up, and then you start seeing the structure of the rim. And as it goes further, for very huge craters, you see actually not only one, but there are like certain many number of rings. So basically, based on the shape of the crater, we can actually divide it into different. I mean, we have given different names to that. I won't go in detail because I can see now I already spent quite a lot time. So basically, because in case of moon we have samples and we have done isotopic dating, we know very precisely what is the age of certain samples. So from that, actually, we have now created a chronology where we say that from the oldest to youngest, and this is based on some major event happened. So we say, so Nectarian is a basin. So we say that pre-Nectarian time, Nectarian time, then Imbrium basin time, Eratosthenes crater. So this crater formed at a certain time, and the Copernican time, which is the youngest time. So the boundaries of these time scales are related to large impact events, and that have modified or may not have modified the surface. So there are like, so basically this is what people do. And there was a question in the first talk that how people estimate age. So basically, because we assume that we actually know the flux of impactor, and once you know that, basically if you count number of craters, you can actually relate it with age. So it's a kind of a mathematical way or a statistical way of estimating age. But because it works in case of moon, because we have samples, and this can be actually applied to inner solar system bodies, because the flux of impactor is kind of assumed same for all inner planetary bodies. So this method has been calibrated using ages obtained from radiometric dating, and that's why we have actually confidence. So I won't go in too detail to this, because again, sort of time. And then this is how, if you look topography of moon, it looks something like this. So it has extreme elevation, plus 8 kilometers, and minus 10 kilometers is almost the same as the dynamic range of earth. So the highest mountain on earth, Mount Everest, is of almost the same range. So but earth is actually it's actually diameters, it's almost 4 times bigger than moon. And this is again a question that how moon can actually keep such a high elevation. So topography itself tells us a lot. There is like a lot of variation we see from very low to like almost smooth plains, and then very very high mountains. Uh, so it has a lot of variations. Now in terms of future missions, one of the main reason to look to moon is to exploit its resources. So if we talk about resources, helium-3 is a resource which is actually in a limited amount on earth, but it is much more available on in case of moon. So basically, very early observation was that the helium-3 is actually related to titanium, and that is based on the sample analysis. So wherever we had actually titanium rich basalts, we actually found that we have maximum concentration of helium. And based on this relationship, we come up with an empirical way of creating a global helium map. And you can see that it actually correlate with titanium map, and wherever we have lava flows, there we actually get helium. But just to keep it in mind, it is still in ppb level. But it is still, if you compare with earth, it is actually amount is actually much more in comparison to Earth. But like getting it from there is another question. It's actually a question for our future missions. So, like before, we had site specific work, we had site specific lunar samples, and now because we have a global data set, we have orbiters, and we are getting the coverage of Moon in a different geometry. This actually give us hands on like creating global maps. So this is a first global space weathering map, and that shows you that some areas like this, the what we already discussed, Tycho crater or crater here, Copernicus crater. These are the craters which are actually, so all these fresh craters and rays, you can see that this is actually relatively young compared to this old highland. So this kind of so this kind of the work what actually we can do with the new data sets available to us. Another example is the global elemental map, and I have contributed in this direction. So now with Chandrayaan 1 data, actually we have, because we have global coverage, there is a way of like indirectly estimating major elements, iron, sorry, the the legend is not very clear, but it's basically iron, calcium, and magnesium maps. So just as soon as we have these maps, we start understanding that how the distribution is, and does it tells us something more about the internal structure or the evolution of the planetary body. So just in the very last, what are the main objectives of ongoing missions? So we had Chandrayaan 1 mission, and now we have Chandrayaan 2 mission in orbit. Basically, the it is still an open question about origin, and we want to understand the origin and evolution of the moon. Uh, we want to we want to apply new technologies and develop and demonstrate that, which can be actually further applied to other planetary bodies, especially Mars, where we want to land and we want to colonize Mars. So again, Moon is a kind of a test bench where you can actually, because it's not too far, if you go to Mars, you to return back from there, it takes quite a while time. But if you go to Moon, you can come back in few days. So if there is any issue also, it's actually easy to resolve in case of Moon compared to Mars. So basically, this is a place where we can actually test our technologies, and then we can have simultaneous mineralogical, chemical, and photogeological mapping at very high resolution. Because if you want to land there, you really need to have very detailed maps and detailed understanding. And for that, actually, the first step is to have orbiters, and the have the high resolution maps of, or the global maps of refractory elements, as well as to explore volatiles, because now the main objective is to go to poles for all our future missions. The main concentration is pole. So to basically have polar, I mean, to under, because these are the areas we have not yet explored much, and we do not have very good understanding of this area. So that is another thing what we would like to actually explore using ongoing missions. And another objective is also to have to actually, what as a part of this webinar, what we are doing is to motivate young minds to take up space and planetary science as their profession, and to basically uh, ultimately to have I mean, it's like science plus technology go hands in hand. So we have certain scientific objectives, and then we look for technologies. If we do not have, we develop that. So it's like it's always like from both sides, we keep actually improving in that. So that is the end of my talk, and I would like to acknowledge that matter as well as pictures in this presentation. I have tried to put it wherever like reference I can, but still, I want to acknowledge that this has been taken from various books, journals, and websites, and I'm grateful to authors and contributors of this source materials. Thanks.